So you can join to the class because we do some in-class activity again. You can join with your cell phone, uh, classpoint.app. You can scan this QR code, or you can go to this website, classpoint.app, and then this is going to be the class code 22568. Okay, you don't need to use your real name. Okay, so okay. Electromagnetic waves. What are the electromagnetic waves? So electromagnetic wave, if we want to just explain it with a very simple language, so electromagnetic wave is a wave that they carrying energy, electromagnetic energy. And what is the energy? An energy carrying wave emitted by vibrating charge. We have particles sometimes. These particles, they are neutral. What does it mean? It means that they don't have charge. But sometimes they have charge, positive charge and negative charge. So we, in this physics, okay, you will not study the electrostatic, okay, electrostatic physics. But you should know that we have particles. Good. We already talked about the motion of the particles. When we are talking about the electrostatic, it means that each particle, you analyze the motion of each particle with its characteristic. How each particle can have positive charge or negative charge, or particle with a neutral charge, no charge. Good. So if this particle that we are analyzing it has positive or negative, it doesn't matter. It will have electric field. So what the electric field means? It means that if we place any other particle with positive or negative charge in the electric field, that electric field exert force on that particle. Good. So, but again, we will not go more details about this. You should know that we have a particle. Each particle which is not moving is stationary. Momentum of that charged particle, it doesn't matter, is positive or negative. So it does have electric field. When this charged particle start vibrating, you remember we have a spring, and then the object attached to the spring moving up and down. We said that this is a vibration, and we can analyze the motion of this periodic motion with a wave. Good. If we have a charged particle and these charged particles start vibrating, not only it create the electric field, but create the magnetic field as well. Because it does have a periodic motion, is vibrating up and down, okay, microscopically. You cannot see a charged particle moving up and down. Good. So if it's more vibrating, not only does have an electric field, but have a magnetic field as well. Because it's moving like back and forth motion, these electric field and magnetic field look like a wave. So as you can see here, as you can see, this one is a magnetic field, and the blue one is the electric field. And we can explain them like a sine and cosine, like a wave. Yes, we already know why we are using wave. any periodic motion, any back and forth motion, we can explain its characteristic with a wave. Electric field and magnetic field. Good? The combination of these two fields is electromagnetic waves. And these is carrying energy. What energy? Electromagnetic energy. Okay? So again, how the electromagnetic wave is created? If you have a charged particle and this charged particle start vibrating, it creates the electromagnetic waves, and electromagnetic waves, they carries energy. So whenever we are talking about the wave, we will talk about the amplitude, wavelength, frequency, the velocity of wave. Yes, whatever we have learned in unit 3, we will try to use those tools here to analyze the electromagnetism wave. Good. So any wave, we know it does have a wavelength, period, frequency, lambda, okay, or the wavelength, and also the velocity of wave as well. Okay. So electromagnetic wave velocity. You should know that it, let me just explain. Okay, when we said that we have an electromagnetism spectrum, the light, visible light that we see everywhere, green light, blue light, whatever we see, it is a small portion of a big electromagnetism wave spectrum. Electromagnetism spectrum start from the radio waves and end with the X-ray and gamma ray, or start with the gamma ray and X-ray, okay, and end with the radio wave. Radio waves will have a longer wavelength but a smaller frequency, but X-ray and gamma ray will have a big frequency but a smaller wavelength. So that's why we try to transfer the sound wave with the radio wave. Why? Because it does have a longer wavelength. Good. But let's say if you have a gamma ray source, if you place in this building, in this room, if you go 100 feet away from this room, you may not receive any wave from this gamma ray source. So that's why I say the gamma ray or X-ray, it does have a smaller frequency, sorry, a smaller wavelength. Good, and we already know what is the wavelength. But bigger or higher frequency, but radio wave, longer wavelengths and smaller frequency. Good. So the energy of the electromagnetism wave is directly related to the frequency. Let's say we have two sources of the electromagnetism wave, gamma ray source and radio wave source. Okay? If you stand in front of this source, okay, which one is harmful to your body? Gamma. Why? Because it does have a higher frequency and the energy is directly related to the frequency. Higher frequency, higher energy. Your body receives a bigger energy, okay? Good? So, and it is harmful to your cells. Okay? The body cells. But the radio wave is, and we have a radio wave everywhere right now, okay? We are kind of bombarded with all radio waves. It doesn't mean it doesn't affect your body. It does affect, but it is very small energy. Your cells, body cells, and your body receive a small electromagnetism energy. Good. So, as I said, the electromagnetism wave have a big spectrum. Start from a radio wave to gamma ray in X-ray, and the visible light that we see is a portion of the electromagnetism wave. So, velocity. You should know that it doesn't matter. The electromagnetism, okay, is radio wave, visible light, X-ray, gamma ray, ultraviolet, infrared, all all will have the same velocity, and this velocity is the velocity of light, visible light. And what is the velocity of visible light? It is 3 times 10 to the power of 8 meter per second, or 300 million meter per second. Okay? You may say, what was the velocity? The velocity was frequency multiplied by lambda. Okay? And we said that the velocity of the light electromagnetism wave is always this number, yes? Is always a constant number, 3 times 10 to the power of 8 meter per second. So if the frequency increase, yes, the wavelength should be smaller. For instance, the frequency of the gamma ray, X-ray is high, but its wavelength should be small, because radio wave and gamma ray and X-ray will have the same velocity. It doesn't matter. The all electromagnetism wave will have the same velocity. So, for instance, X-ray, gamma ray, okay, will have a higher frequency, a smaller wavelength, but radio wave has a smaller frequency. Because it does have a smaller frequency and the velocity is constant, it will have a longer lambda, or the wavelength. Good, this is how we can analyze, okay? Again, the frequency and the wavelengths of the different electromagnetism wave. So, I was talking about the spectrum of the electromagnetism wave. As you can see, it starts with the radio wave, and then we will have a microwave, infrared, and you see the visible light? A very short spectrum, a very short frequency. The spectrum of the frequency is for visible light. When we are talking about the visible light, it means that, red, blue, green, because these are the light, yes? These are the wave. These are the light that is created by vibration of the particle. Let's say if you have a charged particle here and you are starting vibrating this charged particle, you can create the light, visible light. And it depends on how much energy, how much is moving up and down. Because when the object is moving, it does have a kinetic energy, yes? Any moving particle does have kinetic energy. Kinetic energy is kind of directly related to the thermal energy. Right? When the particle starts vibrating, its kinetic energy could convert to the thermal energy, and thermal energy, and then the particles start, radiating a different color. That's, we call it visible light. So, but electromagnetism wave, it does have a broad spectrum. It starts from the radio wave, and then, as you can see, we have X-rays at the end, which a combination of the ultraviolet and gamma ray. when we are talking about the visible light, the three lights, okay, that we see everywhere more than the other light, okay, is red, green, blue, yes, and the violet or blue, okay, so okay. Now we focus just on visible light. If you are interested, you can study the radio wave, microwaves, infrared, X-ray, gamma ray. As I said, we use the application of the X-ray a lot in our daily life. What is one of the application of the X-rays? In pulse, yes? Imaging. It's used for imaging. It's used for radiotherapy. You have heard a lot that those people who have cancer, they just do the radiotherapy. What is the radiotherapy? And they use the source of the electromagnetism wave, which is radiating X-rays. Can be gamma ray, okay? Because each one of these have different level of energy, different frequency, yes, different energy. Sometimes we use gamma ray with a specific spectrum of energy. And what happened? These energy in the wave bombarded toward to this cancer cell, and it will kill the cancer cell. That's why we call it, okay, one of the application is just using the, X-rays for therapy and imaging. If you are interested and you haven't selected your term paper topic and you would like to change your term paper topic, this is one of the very, very interesting area. And I personally did my master in nuclear physics, and a kind of expert in this area because my thesis was to produce my master thesis was to produce iodine 125, which is a radiopharmaceutical and is used for diagnostic and diagnostic of the prostate cancer, okay, which is mostly for imaging part, but it's used for the radiotherapy as well. Okay, now we just focus in these physics, we will just focus visible light. Okay? So we will start with the transparent material. Okay. So what is the transparent material? Material through which light can pass in a straight line. It's called transparent material. So you see in this graph, we have a glass. Yes, we have a glass and we have a visible light. Ultraviolet, visible, and we have electromagnetism wave. Okay, ultraviolet, visible, and infrared. So what happened to these two, ultraviolet and infrared, when they reach to the glass? They stop. So these transparent material just let the visible light pass through the glass. We call these transparent material. Okay? The material through which light can pass in a straight line is called a transparent material. What exactly happened? So what is the process here? You see, what is the process here? This process is just explained, here. how the light pass through the transparent material. Visible light, I mean, okay? Not the other two light, ultraviolet and infrared. So these two come here, okay? Ultraviolet reach to the glass and it's absorbed by the glass. If you touch the glass, good, you will see, if you touch the glass when it is in front of the sunlight, when you put your hand, you will see it gets warm. Why? Because these two light, ultraviolet and infrared, which is a part of the electromagnetic spectrum, absorbed by the glass. And we already said that each one of these light carry the energy. If it cannot pass through the glass, it absorbed by the glass. If you put your hand, you will see that it gets warm. Why? It's because of these two light and other light as well. But visible light pass through the glass. What exactly happened? I can show these, process here. The glass is created with different molecules, atoms, particles, yes? Good. When the light reach to the first atoms in the glass, what happened? The light transfer its energy to the first atom. Okay, you remember? I exert force on this monitor. What exactly happened? The monitor started vibrating. See? It is exactly the same thing happening here. The light, visible light, carry energy. Energy reach to the first molecule. Molecule start vibrating. Yes? When the molecule start vibrating, you remember I said that electromagnetism wave is created by vibration of a charged particle. This is start vibrating. When it start vibrating, again another light. But here is going to be the visible light. Why? Because the energy that this particle receive is the energy in the range of visible light energy. Okay? That's why if this particle start vibrating, it vibrate and create the energy in the range of energy level of the visible light. So it's produce light, yes? And this light goes to the another molecule. Okay, see? Another molecule. And this molecule start vibrating. Okay? When it start vibrating, light created and the light transfer, visible light transfer its energy to the last one, yes? The last one is start vibrating and then create the visible light. Yep. So this is the process. Visible light comes see the first molecule, first atom. The atom start vibrating. The atom create the light again, and this light transfer to the second one. The second one start vibrating, create the visible light. Visible light transfer to the last one. The last one start vibrating again. We have a visible light at the end. This is the process of a how the visible light pass through the transparent material. Make sense? Did you understand the concept? What exactly happened? Now, what you can do, you can go and just pick a piece of glass, put it in front of the light. When you put your hand, after a couple of minutes, when you put your hand, you see that the glass gets warm. It's because of the other, other, it's because other electromagnetism wave absorbed by the glass. That's why you receive energy. And what is the form of the energy? Thermal energy. But if you stand in other side of the glass, you see still light, yes? But let's say if you put a black material in front of the light, what happens? Absorb. Nothing you can see. But if you place the transparent material, other wave, light absorb, but what pass is the visible light pass. So what is the transparent material then? The transparent material absorb, pass just the visible light, but absorb or reflect the other electromagnetism wave or lights. In physics, we call this material transparent material. Good? And we know the process of, passing the light through the transparent material. This process. Vibration, light. Vibration, light. Vibration, light. We will have the light on the other side. Opaque material. Material that absorb light without re-emission. It's called opaque material. That's why you have a shadow. You see shadow. How the shadow is created, or we call shadow umbra or penumbra, okay? Umbra is the complete shadow, darker, and penumbra is just combination of partial shadow, okay? It means that the light, some light pass, some light block. Good? We call it umbra and penumbra. So what exactly happened? How we can see the shadow? What exactly happened? So let's say I stand in front of the sunlight, okay? The sunlight reached to me and I act as a opaque material because I doesn't let the light pass through my material. If the light doesn't reach to the ground, what happened? It's gonna be shadow. Yep. Because everywhere in the world is opaque or transparent. I personally, okay, and everyone, like human body, is acting like opaque material. So what happened? The light doesn't pass, the light absorbs, and the ground, the reason that we see the ground is because of the light. When there is no light, okay, there will be a shadow, yes? So this is how. So the reason that we have a shadow is because of the, opaque material, the material that absorbs the light without re-emission. What does it mean, the emission? Okay, emission was this. Okay, so it is stopped here. It doesn't, bouncing, that energy is not, vibrating the atoms. Because it's not vibrating the atoms, okay, it stopped. Absorb the energy and that's it. It's become hot, okay, and after a couple of seconds or minutes, okay, it's become cold. The energy transfer to the environment. Good. So we have transparent and opaque material. And we know what exactly these two materials are. So now we start our first example. You remember we said that the speed of electromagnetism wave, it doesn't matter, is visible light or other light, like if infrared, radio wave, whatever. So the velocity is 300 million meter per second. This experiment, who calculated the first time the velocity of light in 17th century, okay, 1675, a Danish astronomer, Oles Roemer, measured the velocity of the light. How? By using a Jupiter moon. Jupiter that has its own moon. Okay, if you are interested in astronomy, I don't want to explain too much about this, okay, but if you are interested, you can. Jupiter's moon. He saw the Jupiter's, and he just tracked the Jupiter moon's appearance. Okay, Jupiter moon is acting like an opaque material. Okay, the sunlight, when the person was in this astronomer saw the light, okay, he was able to just use this calculation and to calculate the velocity of the light. The distance from the Jupiter moon was 300 million kilometers per second, and the time that the light passed from one side of the Jupiter moon to another side was almost 22 minutes, which was 990 seconds. When he did this, he was able to calculate the velocity of light. And he was the first person who calculate the velocity of light. Okay, it's not accurate, okay, but the accurate one is 300 million meter per second or 300,000 kilometer per second. What he calculated, it was 303,000 kilometer per second. Okay, there was a little error, but when 1675. Okay, this was example number one. Okay, so again, how we are using the what formula that you have used for exam 3, you will be using for other examples as well. Let's start with the example number 2. We have a sun and its distance from the earth is 1.5 times 10 to the power of 11 meters. How long does it take for the sun's light to reach to the earth? How long does it take the light to cross the diameter of the Earth's orbit? Compare the time with the time measured by Romer in 17th century. Problem number 1. Okay, he did 303,000 kilometers per second, and you're supposed to do this. The sun is this. Okay. If you want, you can upload your responses here. Again, the velocity is distance over time. Yes? So you have the distance and you have the velocity, yes? And you can calculate the how long does it take light to cross the diameter of the Earth's orbit. Did anyone Okay. Anyone uploaded? Okay. Okay. Yes. Okay. So let's see how it's calculated. Again, the distance is how much? 1.5 10 to the power of 11. Okay. And the velocity is 10 to the power of 3 times 10 to the power of 8 meter per second. One thing that you can do is just using your calculator, okay, graphing calculator, and exactly type this scientific number, 1.5 times 10 to the power of 11, and then divide it by 3 times 10 to the power of 8. Or you just use your knowledge, okay, from the algebra. 10 divided by 11, these two you can divide together. Yep. It's going to be 10 to the power of 11 minus divided by 10 to the power of 8. It will be 10, 11 minus 8. Yes. And 1.5 divided by 3 is going to be 0.5. Good. So it's going to be 0.5 times, what is this? 10 to the power of 3. 0.5 times 10 to the power of 3, it means that 0.5 times 2,000. Yes, it will be 500.
How did you get 3 times 10 to the 8?
3 times 10 to the 8.
Speed of light.
No, speed of
Oh.
light. We already have the speed of light. Okay, I said that, speed of light. Okay, at the beginning, I said the speed of light. We calculated, and it is 10 to the power of 8 meter per second, or 300 meter per second. Good. Okay, next question. Next question will be, okay, please just think about this one and upload your answer. Okay. Again, you should, so for some problem, you should use your knowledge from unit 3. Velocity is frequency multiplied by lambda, and the velocity of the light or electromagnetism wave or any light is 3 times 10 to the power of 8 million meter per second. Here in this question, if you see the question, it's telling the nearest star beyond the sun is Alpha Centauri, 4.2 times 10 to the power of 16 meter away. If we were to receive a radio message from that star, how long does it take? Again, radio wave, visible light, other light, they have all same velocity, 3 times 10 to the power of 8 meter per second. We have a distance, we have the velocity, yes? And what was the other velocity formula? Velocity is distance over time. Good? We are supposed to calculate the how long does it take. We can write d equal d over velocity. Okay? So let me just check. 4.2 times 10 to the power of this. Okay, yes, divided by 3 times 10 to the power of 8. Yes, that's the right answer. Thank you. And we have 4 point. Okay. Please, when you are calculating, okay, this is not acceptable. You need just show, okay, what is this? It means that you are dividing these two numbers, multiplying, adding, okay? So you should show how you have calculated. Okay, 3 times 10 to the power of 8 meter per second is equal to 4 times. In mathematics, this is not right. Okay? So what is this? 4.43 calendar years. Yes. Okay, this is the other way to calculate. Okay. Good. That's again 4.2 times 10 to the power of 6 meter divided by 3 times 10 to the power of 8 meter per second, which is going to be 1.4 times 10 to the power of 8 second. If you convert these to year, it's going to be 4.4 years. Okay. How we can convert these? We know that one day is 24 hours. Okay. One day, how we can convert these? Okay, let me just show you if you want to convert the second to the year, because 1 year is how many days? 365 days, yes? And then 1 day is how many hour? 24 hour, okay? And 1 hour is 60 minutes, and 1 minute is how many seconds? 60 seconds. What we do, we can say, we just try to find, to see how 1 year is how many seconds. Okay, so what I do, or 4 point, yeah, 1 year is how many seconds, and then divide that number to, this number to 1 year, okay, to see in second, to see how many year we have. 1 year is gonna be, so 365 days time 24 hours time 60 minutes time 60 seconds. Yes, when you multiply these, okay, it's give you 1 years in second. Good. Okay, when you have this number, you can divide this number by this number. Okay, it will give you 4.4 years if you are, if you would like to calculate, but the right answer is 1.4 times 10 to the power of 8 seconds. If you get this answer, you are correct. But if someone is alpha century and is trying to send a radio wave, for instance, you are using your cell phone to contact with someone on the earth. When you say hi, you have to wait 4.4 years to hear the hi, and then another 4.4 years to person say another hi. Okay, so it takes 8.8 years to send and receive. Just two words, hi, hi. Good. So now this problem, please work on this problem. Blue-green light has a frequency of about 6.6 times 10 to the power of hertz. Now we have the frequency. Now we are supposed to use this formula. Frequency is 6 times 10 to the power of 14 hertz. Use the relationship, which is the velocity equal frequency time lambda, and find the wavelengths of this light in air. How does these wavelengths compare with the size of an atom, which is 10 to the power of negative 10 meter? The size of atoms is very small. It's in size of nanometer, okay, which is 10 to the power of negative 10 meter. So if you calculate the wavelengths of blue-green light and you compare it with a atom size, you see exactly why we will have a light which pass through the transparent material. Go ahead and submit. Okay. Yes. No. Okay. Again, see, we are supposed to calculate the lambda. Lambda is velocity over frequency. Yes. So you need to divide velocity by the frequency. But here we have lambda is equal to c over f. Yes. Again, velocity or v or c, or it doesn't matter. 3 times 10 to the power of 8 meter per second divided by 6.10 to the power of 14 hertz, which is going to be 5.10 to the power of negative 7 meter. Okay. Okay, great. Thank you. And please make, when we are doing the activity, make sure everyone participates. Even if you are submitting wrong, that's all right. I can see what you did wrong, then we can explain about it, okay? So, yes, this one is good as well. 3 times 10 to the power of 8 divided by this. Okay, this is going to be 5 times 10 to the power of negative 7. Okay, I'm closing the submission. I forgot to award. So let's see the answer. Yes, it's going to be 5 times 10 to the power of negative 10. And then you see the 500 nanometer. Nanometer is 10 to the power of 9 is 1 nanometer. Good? So 5 times 10 to the power of negative 7 meter. Okay, I can say 1 meter I know that 1 nanometer, okay, 1 nanometer is 10 to the power negative 7, okay, so if you convert these, okay, to nanometer is gonna be 500 nanometer. Okay, so there is another example number 5 that you can do at home, okay? So again, it's using exactly the same concept, but make sure to, when you are at home and you are reviewing the material, okay, just do this example by your own, which the solution is available. And what you can do, you can go ahead and okay, so selective reflection. As we said, we have a visible light. But the visible light itself is the spectrum of the light from the red to the violet. Good. So we have a visible light, but the visible light itself has the spectrum of the light with different frequency, start from the red to the violet. Okay. So, and when we are talking about the selective reflection, it means that the color that we see are because an object reflects those color and absorb all other. So, visible light reach to our body. Good. My shirt, t-shirt, okay, my hoodie. What color you see? You see blue. But we have a spectrum of the color from red to the violet, red, green, yellow, blue. But what you see, you just see the blue one. What does it mean? The reason that you see is because the light is reflected from the object. That's why you see that color. So why you see the blue one? Because the other color is absorbed by this opaque material and just the blue one is reflected. That's why you see my hoodie as blue. Okay, we call this selective reflection. If you see the flower with different color because the light reach and all visible light is absorbed, but the color that you would see is reflected. That's why you see that color. Good. And it depends on the frequency of the resonance frequency. So the lights come to the flower and then start vibrating the atom and molecule in the flower, and some is absorbed, some is reflected back. The frequency which is reflecting back is the frequency that it's reached to your eye. So let's say if it's red, you see red. If it's blue, you see blue. For instance, in this one, as you can see, sometimes you see glasses with the blue glass or green glass, a colorful glasses. And again, it's follow the selective transmission. Sometimes we have a selective reflection, sometimes we have a selective transmission. Instead of reflection, okay, so the light, all color, the spectrum of the visible light, red, orange, yellow, green, blue, violet, reach to the glass, is absorbed by the glass. Good. And then the only one which pass through is going to be the blue. That's why we see the blue glass. Sometimes we see the glass, and it depends on the opaque material that we use here. Okay. Okay, mixing color. As you can see here, we have red, orange, yellow, green, blue, violet. And now we would like to just explain about if we mix the color, what different form of the color we can get by mixing the color. Because the spectrum of the visible light are these colors: red, orange, yellow, green, blue, and violet. It starts from the less frequency to the higher frequency, or higher wavelength to the smaller wavelength. So here we just try to add the color, but we use three colors: green, blue, and red. Why we are using these three, blue and red? We call these three colors primary colors, because when we just analyze the brightness of the color based on their frequency, we will see that the red, green, and blue has more brightness than the other colors based on their frequency. Okay? And this graph is kind of shows the, the frequency versus brightness or intensity of the light. Okay, and as you can see in this spectrum, okay, is start from the red, but red and green and blue has more portion of the other visible color. So right now we would like to add these three colors. That's why we call these three colors, which does have more intensity, uh, primary colors. Now we would like to add these colors to see what we can get. So for this purpose, I just go to this website. So let me just stop this. Okay, we don't need this one right now. Light mixing. Okay. So I would start and mixing each color together. Okay, so to see what color we can get. We have a red and we have green. If we mix these two, what we will have? Yellow. Okay, red and green, when you mix, you will get a yellow color. So we call the yellow color subtractive color. And if we add green and blue, we get cyan. Okay, so green and blue is going to be cyan. Red and blue is going to be magenta. Okay, so what happens if we mix these three primary colors? White. See here, you know, red and green is yellow, yes, and red and blue is magenta. Blue and green is cyan. You see here, the cyan is the opposite color of the green, the red. See, the cyan is the opposite color of the red. The magenta is the opposite color of the green. And yellow is the opposite color of the blue. Okay? So you should memorize these. Okay, so red and green, yellow, red and blue, magenta, and green and blue is going to be the sign. Okay, so overlap, this Thursday is going to be just mixing this color. Okay, light and also with paint. Okay, so we have three, we just created three subtractive color: yellow, magenta, and cyan by mixing these primary color. So by adding primary color, we will get, by adding all three primary color, we will get white color. Let me just Google color mixing. Again, okay, you can use different, it's going to be exactly the same thing. So as you can see, so you can use different website or this website or physics.com and then this website and to just, and if you can just change the intensity of the red. You can change the intensity of the green. Yes, see, you can change the intensity of the blue, and you will get, for instance, if you are getting a cyan, you will get cyans with the smaller intensity, less intensity. Good. And then the same thing. So let me just show you. Okay, so now we have a three subtractive color. What happens if we add the subtractive colors? So red and red and blue is what? Magenta. Red and green is
Yellow.
yellow. Yes. And then green and blue is cyan. What I do, if I add these three, yes, I will have what? Red, green, blue. I will have white, yes. But if I add three subtractive color, what will I get? Magenta plus yellow plus cyan. What I get? Perfect. Black. Okay. So we can use this technique, okay, subtracting color or adding color or mixing color in, you have seen in a concert, okay, so concert hall, they use different color, mix color, and even color, they create, colorful shadows, okay, so they are using this technique. So again, you can use that website, okay, and learn about it. So by adding a primary color, you will get why? By adding the subtractive color, you will get dark color. Okay, so it means that they are all will be. We talked about the intensity. Here we will have a magenta, yellow, and cyan. If we add, see, if we have now yellow, and then if you add, all subtractive color, so you will get what? Black. But if you add yellow and cyan, you will get green. If you add magenta and red, you will get, sorry, magenta and yellow, you will get red. If you add magenta and blue, you will get cyan, you will get blue. Yep. So again, these are, from now we will talk about the colors that we see in the sky. So for instance, why the sky is blue? And the reason that the sky is blue, because as we just explained, we have a reflection and absorption. What we have learned? We have learned about the light reflection and the light absorption. The reason that you see the sky blue because the light, the sunlight reach to the air atmosphere, yes, and then all color will be absorbed, but the only color will be reflected or transmitted is kind of violet color. Okay, because our eyes is so sensitive to the blue one. Okay, that's why we see it blue, not exactly violet. But but you need to know that when the spectrum of the light reach to the air atmosphere, some visible light will absorb by the air atmosphere. Good. The only one which is reflected or scattered is the violet. Because our eyes is sensitive to the blue one. Okay, we just see the sky as blue. Why sunsets are red? So in the middle of the day, you see the sky blue, yes, and then the light is just the light, okay, white light, okay, visible light. But during the sunset or sunrise, you will see red color or red yellowish color more than any other time. Why? Because more light is being scattered by the atmosphere, okay, the air atmosphere. For instance, when we are in the middle of the day, you see the air atmosphere, okay, the atmosphere of the earth, see, just the light, see this portion. But when it is a sunset or sunlight, it will see a big portion of the atmosphere. That's why it's absorbed the other color and then scattered the just a red or yellowish one more than any other one. So that's why during the sunset we just see the light or visible light as a red light. Why clouds are white? As you know, the clouds are made of water droplets in various size, different size. A small droplet scatter the blue frequency, medium droplet scatter a green frequency, and large droplet scatter red frequency. Good? So since all frequency end up getting scattered, good, we have blue, green, and red. The size of the cloud droplet, yes, water droplet, is important. What color, okay, will be scattered? If it's a small size is blue, medium size is green, okay, a big size of the water droplet is going to be red. Because we have combination of these three. When we add these three, what we will get? The white. Okay, that's why we see the cloud white. So again, about the water, okay, is exactly the same. Okay, you can just read by your own. And we already talked about the light emission, why we have a light emission. And as I said, if the charged particle receive light or receive energy and is a start vibrating. When is it start vibrating? Again, we will have electromagnetism wave. If the energy that that particle receive is in the range or frequency of the visible light, it emits a visible light. If it's in the range of other frequency, it will emit X-ray, gamma ray, infrared, ultraviolet. Good? So, but the energy that these particle emits, how we can calculate this energy? By using this formula. Okay, E is equal h times f. What is the h? Is a constant number. We call it Planck constant. Planck constant is a constant number, but E is the energy and F is frequency. You remember I said that the energy of the light emission light is directly related to the frequency. Yep. So we have bigger frequency, bigger energy or emission, bigger energy. The emission, the light emitted, okay, will have a bigger energy. Okay. So because we have a color in different frequency, each color will carry different form of energy or different. So because each color will have its own energy level, so we will call these a photons of energy, a quanta of energy. Okay. So different colors of light are due to different frequency of emitted photons. Okay. Emission spectra or spectrometry. Spectrometry is a very interesting technique. Again, if you would like to change your term paper topic, okay, this is another topic which is really interesting. And a spectrometer. What is the spectrometer? A spectrometer is a tool that helps us to understand what materials or what molecules or atoms are in one object. Good. So for instance, how you find out about the different material in the different stars. It's by a spectrometry. Okay, what is the spectrometry? We talked about the emission, yes? When the charged particles start vibrating, if you increase the temperature of the charged particle, okay, it start vibrating, okay? And when it start vibrating, it's create the electromagnetism wave. And each particle can emit its own energy. Carbon, sodium, oxygen, nitrogen, any atoms. Okay, any atoms, if you increase the temperature, you are kind of increasing its kinetic energy. By increasing its kinetic energy, it start vibrating and it's create the electromagnetism wave. And a portion of the electromagnetism wave is the visible light. That's how you can analyze these colors and then find out about, okay, what atoms, okay, is creating these spectra. Good. So as you can see in this graph, you will see a brightness of the light and the frequency of the light. Each atom has its own peak. Good. And it changed with the temperature. By increasing the temperature, you would be able to get the different peak and different brightness. Absorption spectra. Absorption spectra is the continuous spectrum interrupted by dark line or bands that result from the absorption of the light of a certain frequency. What does it mean? I will show you a short video and it kind of explain what exactly happened. But let me just explain what is this exactly. So you have a light, and the light, you see this light, the light pass from the lens, and what the lens does, it try to focus the light, and if the light are traveling from the the focal point of the lens, when they pass from the lens, they will be refracted. We will talk about the refraction, but what exactly happened, we will have a parallel light. Okay, you will learn about the refraction, okay, next week. But what happened here, we have a sodium metal, and what we just do, we just start increasing the temperature of this sodium. We have the light, yes, and the light come and reach to the sodium's vapor gas. So there will be interaction between the light and the material inside, the atoms inside, yes? What happened? We will have what we will have, because this carbon does have its own spectrum, yes? From the red to the violet. Good? This visible light, it has its own spectrum. We have its map. You see here, we have a map here. Let's say the carbon, okay, it has its own map. Okay, this is the map for carbon, the spectrum of the light. So sometimes for different material, you will see that the blue is bigger than the red. Okay, so we can map out all particles light spectrum. Okay, so but we already have this map, and we would like to see what exactly is inside this box. We try to increase its temperature. The light come and pass through this box, and what happened? Some of these, okay, some of these particles absorb the emission light, yes, the light, and then when it's reached to this particle, we will have reflection or absorption. Can you listen to me? Emission, it can have reflection or absorption. Whatever is absorbed, okay, stay here, the rest go through the box, yes, and then reach here, and then we will be able to just use this prism and have its spectrum. Good. So what exactly happened when this light passed? Okay, so we will see a small band dark light here. All the small dark line is kind of representing what material is inside this strip. How? Okay, let me just show you a video, and probably you can understand it a little better. Unravel real holiday spirit with Kinder Bueno Mini. Holidays get bueno.
You can pick.
Let me just stop shading for now. When I share computer audio. Now share, and it's recording.
Figure out the chemical composition of a star by looking at the absorption spectrum that it produces. But why do we see absorption spectra from stars? A star is a source of light. Observing its light waves through a spectrometer, we will find a continuous spectrum. A continuous spectrum is made of a continuous range of wavelengths or frequencies. But here is what's called an emission spectrum. There are bright spectral lines against a dark background. An emission spectrum can be produced by a hot gas that is emitting photons of particular frequencies. That is why we don't see the entire spectrum. When we observe stars on Earth, we see spectra like this. This is called the absorption spectrum. Well, what do you notice? This is the exact opposite of the emission spectrum. The frequencies missing from these absorption lines are the emission lines. This means that if we subtract the emission spectrum from the continuous spectrum, then we get the absorption spectrum. These two spectra are categorized as line spectra to distinguish them from continuous spectra. Let's see how this physically happens with a star. A star, like our sun, emits photons of all frequencies to produce.
So what happened? Okay, we have a sun, the light spectra, visible light spectra. Good. So, and which is from the red to the violet. And we have absorption. What is exactly happening inside that box? Yes, the sodium vapor, hot gas. This is the absorption spectra. When you subtract these two, you will have, a map. And this map will help you to see what is exactly inside that box. That's why we call this a spectrometry. This is a technique. And why we use these? Okay, because we would like to see what kind of material is in the different galaxies. Okay, in different galaxies we have different stars with different age. Okay, and at different age they will carry different form of atoms. Good. So these techniques will help us to find out what exactly happening, what kind of a star and which form or type of a star we have.
A continuous spectrum. But before these photons reach us on Earth, some of these photons get absorbed by the cooler gas around the star. The gas then becomes excited, which means that it becomes hotter so that it can re-emit photons, giving us the emission spectrum if we can isolate just the gas and look at it through a spectroscope. But looking at the sunlight that has passed through the gas, then we will get the absorption spectrum. In other words, the photons that form the absorption spectrum are the ones that did not get absorbed by the gas.
Good. So it's really good technique to see what exactly happening. Okay, inside this stuff. Okay, when the light we receive, we have its map already. But when we receive the spectra, we will see a dark line. Okay, those dark lines will help us to find out what kind of material is in that stars. Yes? Okay, this was the spectrometry. If you are interested, and this is a really good topic if you would like, you can pick for your term paper. So, and fluorescence lamp, okay, so for spectrometry, we use a different lamp. So because we need to just create a light, yes, visible light. And how we can create the visible light by increasing the temperature of the atoms. And by using, these lamps, we would be able to create the spectrum of the light. Okay? So, and we have different, lamps that we can use for the spectrometry. And so lasers, I will explain about the lasers, okay, in the optic, okay, so, but what is the lasers? Light amplification by stimulated emission of the radiation. Because if we could use a technique, because when we have a light source and this light, visible light, travel in 3D, yeah? If we could manage this light and just focus it in one line, we would be able to create a laser light. Okay, which is called, okay, laser stands for light amplification by a stimulated emission of the radiation. But I will talk about this, but just letting you know what is the laser, but I will talk more about the laser in the optics section, which is going to be not next week, the week after. Okay, so we are done for with today's class.